Artificial intelligence creates a basic problem for policymakers. Government is built to manage things that can be measured, categorized, placed on a timetable. Laws have sections, budgets have numbers, programs have milestones, agencies have jurisdictions. AI does not fit comfortably into that world. Its capabilities appear to advance along curves that are difficult to visualize and even harder for institutions to match. The model improves. 6 months later, it can perform tasks that previously seemed years away. Then those capabilities are embedded into millions of products, copied across borders, and connected to other automated systems. To many people, this feels less like ordinary technological progress and more like an open-ended growth event. The natural political response is to reach for a break. But history suggests a different approach. Humanity has faced apparent infinities before. Industrialization created what seemed like an infinity of production. The internet created what seemed like an infinity of information. In each case, the successful response was not to stop growth, it was to build new concepts, standards, and institutions that made that growth understandable and usable. Artificial intelligence may represent a third such transition, an apparent infinity of cognition, coordination, and knowledge production. The challenge is not to eliminate that growth, it is to learn how to navigate it. Between roughly 1750 and 1900, the Industrial Revolution transformed the material foundations of civilization. Populations expanded, energy consumption soared, factories produced goods at scales that would have been unimaginable to earlier generations. Before this period, most societies understood economic life as cyclical. There were good harvests and bad harvests. Kingdoms rose and fell. Wealth might shift from one region to another, but the basic limits of production seemed permanent. Industrialization broke that mental. Fossil fuels, mechanized production, interchangeable parts, railroads, and large-scale manufacturing created sustained increases in output. The economy was no longer simply repeating itself, it was compounding. The world did not respond by outlawing factories because their growth was difficult to understand. Instead, people invented abstractions that made the new industrial system manageable. Standardized time allowed railroads, cities, and businesses to coordinate across distance. The metric system replaced a patchwork of local measures with common units. National income accounting eventually allowed governments to summarize millions of transactions into concepts such as gross domestic product. These frameworks did not create industrial growth. They made it legible. When a new technology changes the scale of human activity, the most important policy innovation may not be a restriction, it may be a new map. Industrial growth also revealed another pattern. What first appears infinite usually encounters limits. Resources become scarce, markets mature, infrastructure becomes saturated. Growth that once looked exponential begins to slow and eventually resembles an S-curve. The Industrial Revolution was extraordinary, but it did not abolish scarcity. The late 20th century introduced a different kind of apparent infinity: information. Computing dramatically reduced the cost of storing, copying, and transmitting data. Then networks connected computers to one another. Each new device did not merely add another storage location, it created new possible relationships, new communication pathways, and new opportunities for exchange. Computer scientists used Big O notation to describe how the demands of a process grow as the size of the problem increases. A linear process grows at a manageable pace. An exponential process grows much faster. The networked world sometimes felt faster still because every new participant could interact with many others. The result was not simply more information, it was an environment in which information became effectively abundant while human attention remained fixed. Again, the answer was not to stop the network. Engineers developed TCP/IP so different machines could communicate. HTTP created a common structure for the web. Search engines organized scattered pages. PageRank helped make an enormous and chaotic information environment navigable by using the link structure of the web as a signal of relevance. These tools imposed order without requiring a central authority to approve every website or every connection. Yet the information revolution also reached a limit. Human beings still have only so many waking hours. Storage can expand, bandwidth can increase, content can multiply. Attention cannot grow at the same rate. The constraint shifted from access to selection. Artificial intelligence now changes that equation again. For most of the internet era, humans generated requests and computers returned information. Search engines crawled pages, trading systems executed rules, and customer service bots handled narrow interactions. Automation was already everywhere, but much of it remained specialized and predictable. The emerging agentic web is different. AI systems are beginning to initiate tasks, use tools, delegate work, call other models, negotiate with software services, and operate across long sequences of action. A human may provide a goal, but an increasingly complex network of agents may determine how to accomplish it. This creates the possibility of explosive machine-to-machine activity. Imagine thousands of agents researching, testing, purchasing, scheduling, coding, and communicating with one another. Every agent can potentially interact with many other agents. They can create sub-agents, retry failed tasks, compare results, and continuously monitor changing conditions. The volume of automated coordination could grow much faster than the human-centered internet was designed to accommodate. Some of that work will be technical. Agents will need more efficient communication protocols so they do not waste amounts of computing power talking past one another. Networks and data centers will need to scale. Authentication systems will need to distinguish among people, trusted agents, malicious bots, anonymous automated traffic. The old CAPTCHA model is already weakening. Frontier systems can often solve challenges that were once used to prove a user was human. We may need voluntary proof-of-person credentials, secure hardware-based authentication, or reputation-based systems that allow services to know not only that a request is automated, but who is responsible for the automation. The goal should not be to preserve an internet in which only humans act directly. Bots can create enormous value for the people and organizations that deploy them. The goal is to ensure that human agency is not drowned in automated noise. Policy matters here, but policy should begin with the right objective. Governments should support the infrastructure required for AI growth, preserve competition, and avoid regulatory structures that freeze the market around a small number of incumbent firms. The companies best positioned to comply with expensive licensing and reporting regimes are often the companies that already possess the most capital, data, chips, and political access. A policy intended to control AI can easily become a policy that protects the largest AI companies from future competition. The better role for governments is to establish clear rules of responsibility while allowing markets to determine where capital and innovation should flow. This also requires a realistic approach to AI safety. No complex software system is perfectly secure. Large language models can be surrounded by guardrails, red team testing, monitoring, access controls, and alignment techniques. All of those measures are useful. None of them can guarantee that a system will never fail. Cybersecurity history should make us humble. Highly protected government and corporate systems have still been compromised. The lesson is not that digital systems are useless. It is that safety must be engineered around the expectation of imperfection. AI should be approached in much the same way. Aviation did not become safe because engineers discovered how to build an airplane that could never malfunction. It became safe through redundancy, investigation, simulation, monitoring, maintenance, training, and continuous improvement. AI governance should follow a similar reliability model. In sensitive environments, model outputs may require human review. Critical actions may need confirmation from a second system. Tools should detect and contain the release of classified proprietary personal or medical information. Logs should make failures traceable. Organizations should test not only whether a model performs well under normal conditions, but how it behaves when confused, manipulated, or placed under stress. The aim is not to prohibit all risk. That would prohibit nearly all meaningful use. We also need better ways to measure the pace of progress. In 2025, the research organization Meter described a metric called the 50% task completion time horizon. It asks a practical question. How long would a task take a skilled human when an AI system has a 50% chance of completing that task successfully? This gives us a way to move beyond vague claims about whether a model is intelligent. We can instead ask how long and how complex a task can reliably complete. That horizon has been expanding rapidly. Systems that once handled tasks measured in seconds or minutes are moving toward tasks that require longer chains of reasoning and action. A model that writes one paragraph is a tool. A system that can complete a multi-hour research, coding, or administrative workflow begins to resemble a worker. A network of systems that can coordinate those workflows begins to resemble an organization. Still, exponential trends do not continue forever. AI progress will encounter constraints in energy, chip fabrication, data quality, capital, physical infrastructure, and perhaps the basic architecture of current models. The curve may move from dramatic scaling to slower improvement, but before that happens, the system may still become capable enough to transform a large share of economic activity. That raises a deeper question. When machines complete tasks that once required human effort, are they merely compressing existing knowledge, or are they creating new knowledge? AlphaGo offers one useful example. In 2016, AlphaGo played Lee Sedol in the game of Go, or Baluk in Korean. During the second match, it made what became known as Move 37. The move looked strange to expert observers. Some initially regarded it as a mistake. It later proved decisive. AlphaGo had discovered a useful strategy that human players had largely overlooked. That was not simply faster calculation, it was a form of bounded creativity. The system explored a space of possibilities and found something genuinely new to human understanding. But the word bounded is important. Go has a fixed board, fixed rules, and a clear measure of success. AlphaGo could search for new strategies because the environment told it what counted as winning. Most importantly, human problems are not that clean. In politics, science, business, ethics, and culture, we often disagree about the goal itself. We invent new categories, we change the rules, we create new language, we decide that an old measure of success is no longer adequate. AI systems can explore enormous spaces of possibility, but they still operate within architectures, objectives, data, and verification processes provided by human beings. This is one reason predictions of total human obsolescence are premature. Human beings do more than search for answers. We decide which questions matter. We create institutions, we assign meaning, we redefine success, choose what kind of future is worth building. The most productive relationship between humans and AI will therefore be a co-learning loop. People will guide, critique, and refine machine outputs. AI systems will help people test ideas, explore alternatives, identify patterns, and extend their cognitive reach. The system will not simply replace human thought. It will change the scale at which human thought can operate. That means education must change as well. Students and workers will need to learn how to supervise automated systems, recognize plausible errors, structure problems, verify outputs, and combine machine speed with human judgment. Institutions will need practices that reward effective collaboration with AI rather than pretending the technology can be excluded from modern work. It is whether our institutions can develop the maps, standards, and habits needed to make that growth serve human flourishing. Industrialization gave us an apparent infinity of production. The internet gave us an apparent infinity of information. AI may give us an apparent infinity of cognitive labor. Each transition creates fear because the old categories stop working before the new ones are ready. But the lesson of history is not that growth should be feared. It is that growth must be made legible. We need protocols for agent communication, better ways to verify human and automated identities, reliability standards that assume systems will sometimes fail, measurements that track how much sustained work AI can perform, security tools that contain sensitive information, competitive markets that prevent regulation from becoming a shield for incumbents. Above all, we need confidence in the continuing role of human agency. AI may discover moves that no human would have considered. It may perform years of intellectual labor in a fraction of the time. It may create systems of coordination too complex for any one person to fully understand. Yet it will still be human beings who decide which games are worth playing, what winning means, and how the benefits of progress should be used. Policymakers should not treat artificial intelligence as an alien force that must be frozen in place. They should treat it as the next great terrain of human development. The task is not to restrain intelligence. It is to build the frameworks that allow intelligence, both human and artificial, to expand freedom, prosperity, and human possibility.